I want to talk about what makes reactions spontaneous. And what I mean by spontaneous is the ability to occur naturally, meaning you don't have to force a reaction to happen. So I want to go back to these energy diagrams that we studied earlier, feels like about 50 years ago, and comparing exothermic and endothermic reactions, because so far we've only really discussed enthalpy or the transfer of heat in relation to reactions. And I'm not sure that I took the opportunity to emphasize what nature um, tends to favor. And what I mean by that is what is more natural for chemical reactions as far as the transfer of heat. So I wanted to come back to these energy diagrams to talk about that with you. So here is an exothermic reaction. And you can see that the reactants have more energy than the products. So if enthalpy overall is the energy of the products minus the energy of the reactants, then of course your delta H, your change in enthalpy, is going to be a negative number. And that's why delta H is negative for exothermic reactions. Um, and the one for endothermic reactions, of course, the reactants have a lower energy than the products do. So if you subtract the products minus the reactants, of course, you're going to get a positive delta H. So I just want to take the opportunity here to have you look at these two graphs and think, which one do you think is a more natural thing to happen, an easier thing to happen? Do you think it's easier for reactants to lose their energy and to go to a lower energy state as the products? Or do you think it's easier for reactants to gain energy and form products that have a higher energy state? In reality, nature favors, of course, a lower energy state. That's the whole reason why reactions happen. It's the reason why atoms form chemical bonds, because everything in nature wants to have as low an energy state as possible. Even last year, when I talked about when atoms gain energy and the electrons become excited and they move to a higher energy level and to an excited state, they cannot stay there for an indefinite period of time. Eventually they're going to have to release a photon equal to the energy that they gained and go back to their ground state. So it's the same thing here. So in terms of enthalpy only, exothermic reactions are favored over endothermic reactions, because if everything wants to go to a lower energy state, then of course the exothermic reaction is the way to go. But here's the problem. Ice melting is a naturally occurring endothermic process. Okay, think about that. The ice absorbs the energy from its surrounding and melts the ice. Liquid water is at a higher energy state than solid ice. That seems to go against this theory that exothermic reactions are favorable. Having a negative enthalpy change is favorable, more spontaneous than an endothermic process. But you can't deny that ice naturally melts. It's a spontaneous change. If you take ice out of the freezer and you expose it to temperatures above zero, it will spontaneously melt. So that means that enthalpy cannot be the only factor that affects whether or not a reaction will take place naturally. And if I can go down here and find where I'm at here. So you have this thing called entropy. Okay. So most chemical reactions in nature are exothermic, which means energy is released and the products have less energy than the reactants did, which means the products are more stable than the reactants. Again, the trend in nature is for a reaction to continue in a direction that leads to a lower energy state. But because endothermic reactions do occur, it means that there is something else, a different factor that must also affect whether or not a reaction will take place spontaneously, and that is entropy. So what entropy is basically a measurement of disorder. Whoa, no, I don't want to. No, go away. I want to go away. Okay. Well, that sucks. All right. Well, that was a total fail. Anyway, here we go. I'll just use this. So if you look at the arrangement of particles in a solid, a liquid, and a gas, you can see entropy at work. So in a solid, the entropy is very low because you have to think of entropy in terms of the degree of randomness. How chaotic is it? If it is highly chaotic, it has a high entropy. If it is extremely ordered and not random at all, then it has a very low entropy. So solids have the lowest entropy of the three states of matter. Liquids have a higher entropy, and of course, gases have the most entropy. So entropy is the second factor which affects whether or not endothermic reactions occur. Now, going back to my example of ice, you can use this diagram to think about why ice, an endothermic process, which according to the rules of enthalpy, should not be a naturally occurring process because liquid water has a higher enthalpy than ice does. So why does ice melt spontaneously? It is because of the arrangement of particles. The liquid uh, the solid particles of ice are becoming more random. The entropy is increasing, which is why some endothermic processes do occur naturally, like ice melting. Now let's put it in terms of a bit of a more chemistry and look at a reaction. And how does this relate to entropy? So here's a reaction where we have ammonium nitrate, which decomposes on with heat to form nitrogen gas, liquid water, and oxygen gas. Now, looking at this equation, there's a couple of ways to do this. So first of all, on the left-hand side, you have a substance in the solid state, which decomposes into three additional, or not additional, but three separate substances, two of which are in a gaseous state and one of which is a liquid state. So just based on the fact that you're going from a solid to two different gases and a liquid, that is a huge change in entropy. You're becoming much more random, going from one solid to three separate substances, two of which are gas and one is a liquid. So you're increasing entropy by turning a solid into a liquid and by turning a solid into a gas. And then on top of that, you're turning it into three different substances. Another way that you can look at it is the number of moles. You have only 2 moles on the left-hand side. You have 8 moles. You have 2 plus 4 plus, sorry, 7. 2 plus 4 plus 1. That O2 is confusing me. 2 plus 4 plus 1, 7 moles on the right-hand side. 7 moles is more random than only 2. If it's confusing for you, think about people. 7 people is more random than 2, right? 7 streets is more random than only 2 streets. It's more chaotic. So think about it that way. So what I think I will do is, yeah, I talked about that already. I'll give you a worksheet to practice looking at how entropy changes over different chemical reactions. And then probably upload that video because it's maybe, I don't know. And then we will look at how do you figure out combining enthalpy, which says that exothermic reactions are favored, and entropy, which says that more randomness is favored, because they are not really related at all, but they both affect whether a reaction occurs spontaneously. How do you put those two things together? There is a nice, neat little chemical equation or formula, sorry, a formula called Gibbs free energy, which does that. I'll talk about that later. But a couple other examples, or at least one other example, of increasing randomness. If you have a pure substance like water and you make a solution out of it, that is more random. That is higher entropy. So in this picture, entropy increases even as the sugar molecules dissolve in the whatever that is, tea, I'm assuming. So you can see from the top picture, you've got the sugar molecules that are all at the bottom. Now, keeping in mind that this is still a higher entropy than just the plain, whatever that is, before you've added the sugar, the tea, I guess, or tea bags. So one, You started with pure water, which has very low entropy. Then you made tea, which increased the entropy. Now you've added sugar, which increases the entropy. And as the sugar dissolves and disperses through the liquid, you have the highest entropy for this particular system.